On February 3, 1996, unusually warm water in the western Pacific Ocean gave rise to a moisture-laden air mass. Carried aloft by the subtropical jet stream, it journeyed northeastward. Lowering temperatures in the mid-latitudes caused increasing condensation as the air mass took aim at the western United States. On February 5th, the full force of the storm hit the central Oregon coast.
The weather situation has gotten worse since I spoke with you yesterday, and it's likely to get even worse during the next 2 days. Some rivers are expected to exceed their flood stage by as much as 12 feet. If you live in a low-lying area that has the potential to flood, you need to seriously consider leaving now.
A quarter mile up the road, another slide. As you can see, this one would threaten a home. Carol Royce escaped just in time.
I thought it was over.
I can't even begin to describe how massive it is. I mean, boulders the size of cars, obviously vehicles and victims involved in this, the rail line that goes along this highway. I mean, the rail cars just pushed over like toys.
There'd been a lot of stuff on the evening news, a lot of live footage, but frankly, most of that was not focused on the natural forest. It was more focused on main highways and homes. And I knew that there was a story going on out there in the forest that hadn't been seen yet.
We had about 23 inches of water, about 10 feet of snow up high. We had about 2 feet of snow, about 6 inches of water down low. Here comes this tropical system boogieing out of the South Pacific. It's carrying about 11 inches of water in over 4 days, and bingo, we get a flood.
Oh my God, it's like, it is, it's an aircraft carrier. Look at that thing. Oh my God.
Gordon Grant and Fred Swanson have been studying the hydrology and geomorphology of the H.J. Andrews Experimental Forest for over 2 decades. On the morning of February 6th, Grant got on the internet to check the stream gauging stations.
I saw something I'd never seen before. The Mackenzie was going up about 1,000 cubic feet per second per hour. So the rate of rise was unprecedented in my experience. So we knew something was up, just dropped everything and headed out to the forest. And when we got here, things sort of were pretty much in place. You know, the streams were up, they were muddy, there was a lot of water on the road, rocks kind of falling off and things, but we'd seen all that before. Went out to dinner, and sometime while we were sitting around at dinner, things really began to pop. Came back up, it was dark, and we could see brown ooze flowing over the road surfaces, over the snow, and we knew that at that point that the hill slopes had begun to move.
At first light, they took Grant's video camera to the bank of Lookout Creek below the Andrews headquarters.
I believe you took some shots from this point right here.
Yeah, I came over and I remember being really impressed how that stand of trees out there, that they were still intact at that time.
Oh, here comes a big root wad Rip City.
Whoa!
Root wad first.
Whoa! Ride the wave!
Oh, that guy must be what?
We were very impressed by the power of the storm. In this very location, hearing the big boulders bounce along the bottom. It wasn't tinkle, tinkle, tinkle. It was ka-wunk, ka-wunk, ka-wunk. And watching those very large logs move.
The flood offered them an unprecedented opportunity to study the process of landsliding and the potentially devastating debris flows that result.
Now, debris flows are essentially channelized mass movements. They're where a landslide gets into the channel and becomes this churning mass of mud and debris and wood and rocks and water and charges down slope at speeds of 20 or 30 miles per hour.
Grant and Swanson go to investigate the origins of the debris flow that race down the tributary channel designated as Watershed 3 on the Andrews Forest.
So here's a little innocuous ephemeral channel. Water came down, kept going across the road tread. Some of it spilled over this side and created a gully, ran down. Looks like it created a small slide. It looks like some of it continued on down, would have spread out somewhere in here.
And this water then flowed over to the bank here and flowed into the fill slope. And on February 6th, probably contributed to the occurrence of this very large slide of perhaps several thousand cubic yards, which broke loose here, slopped up on the opposite valley wall, and ran down the channel as a debris flow for about a half a mile, and then ultimately spilled over the road, depositing sediment and woody debris into the main stem of Lookout Creek.
This landscape could be characterized as decades of boredom punctuated by hours of chaos. And these storms are the hours during which much of the work, much of the physical work of the landscape is performed. So the features that we see out here, the bars, the sediment, the very shape of the channel, the position of the logs along the bank, all of these owe their origin to that 12 or 24-hour window during which these channels are in full flood.
To exploit the learning opportunity created by the flood, a group of scientists gathered at the Andrews, where the Forest Service and Oregon State University have maintained a long-term ecological research station for the last 50 years.
What we're trying to do is remap the channel and describe the attributes of these different surfaces and how they've changed in response to the recent flood.
George Linekamper is a geographic information system specialist for the Forest Service.
Think about that. Maybe hold off on actually numbering the surface until you see what it looks like further downstream. The old maps that were done 10 years ago are already part of our GIS. We'll be able to overlay the different surfaces from the two maps and look at the changes of the accumulation of sediment, the movement of sediment, the mobility of wood, and remap the channel for the next storm that comes along.
The value of the work done by scientists at the Andrews is revealed through the long-term records of change. They've tracked the amount of sediment that has moved through the system during normal stream flows and floods for the last 40 years.
We've learned that more sediment comes down during a couple of hours during a flood than for all 40 years, the remaining 40 years combined. And so these really are significant events in terms of changing the channel system, in terms of setting up habitat for organisms, in terms of structuring the basic morphology and energy of the system, and really of moving the landscape, of taking the sediment and the wood from the hill slopes and bringing it down.
A debris flow can be visualized as a series of events with effects that cascade down the system. Already saturated ground is exposed to more rain. The tributary channel begins to flood. Then, suddenly, a hillside gives way on the valley wall. It enters the tributary channel, combining with water as it heads downslope, picking up boulders and logs. It enters the flood in the main stem, a torrent of water, mud, and debris that scours the channel, tearing out trees and streamside vegetation.
I'm not really sure about this maple, but it looks like it might be 17 to 20.
The patterns of change in streamside vegetation tell the tale of past big events. A group, led by Julia Jones, deciphers the story by counting the growth rings of trees.
We have a long-term history of flood records for the last 50 years, and we're interested in whether the big floods created more disturbances or fewer disturbances, and we're trying to trace how big the disturbance was from each of those previous floods by measuring the sizes of the areas that were created according to the ages of the trees that are on them.
The data they gather may help explain the difference in degree of disturbance between the last major flood in 1964 and the flood of '96.
The 1964 flood created a lot of disturbed zones in this landscape, but actually, as a flood, it was smaller in Lookout Creek, where we are today, than the '96 flood, or so we believe. And so we're interested in understanding what it was about the 1964 flood, which may have had less water in it, that caused it to create more disturbed surfaces by comparison to this most recent flood.
We're now in the process of looking carefully at the ecological and geomorphic consequences of the flood of '96, and we're very keen to compare that with the effects of the flood of '64. And our preliminary observations are telling us that the geomorphic consequences of the '96 event were less than the '64 flood in this basin. In 1964, we'd had 15 years of logging and road construction using old road techniques. That led to a whole series of landslides and debris flows down the hill slopes and down the small channels. Leading up to the 1996 flood, we'd had 25 years of virtually no logging and no roading. We have less hill slopes prepared for sliding, and we've had less woody debris in our small channels available to be moved by slides and debris flows. So we've had less disturbance in the main stem riparian zones.
Channels and streams in a natural process are shaped over time by floods. But it's clear that the way we manage the land affects the rate and severity of change. For the last 25 years, the Andrews Forest has been left largely intact. As a result, the '96 flood appears to have caused less damage to streams than the earlier but smaller flood of '64. The storm first hit land in a coastal forest which for 40 years has been intensively roaded and logged. The Siuslaw National Forest is in the Central Coast Range, which receives up to 120 inches of rain each year. It's a lush landscape fueled by moist ocean air, and once was home to some of the richest salmon habitat on Earth. Jim Furnish is the supervisor of the Siuslaw National Forest. He saw the chance to evaluate logging and roads in light of this major event. After the storm had passed, he went out to survey the damage.
And I was struck particularly with some of the road failures, the enormity of the road failures. They weren't just little washouts here and there, but there were some really big slides. We certainly had some clues as to the vulnerability of the roads. I think our first big taste of that came in the winter of 1971-72. I think it was the first exposure that that managers on the Siuslaw had to maybe what we had been doing, there were some liabilities. Bad things could happen. And before that, there was, I think, kind of a, everything was just kind of trucking along. We were building roads and harvesting timber and making a lot of money and creating a lot of jobs. And then all of a sudden that big storm event of 71-72 happened, and wow, it really, we had landslides everywhere.
It's not the fact that you get debris torrents off forested landscapes that's the big deal. Debris torrents happen in old growth as well. But what is different is the frequency, what kind of materials in them, and then how far the effects from those go. That's the big difference.
Charlie Dewberry is a biologist who has worked for several years with the Forest Service and private landowners to restore fish habitat on Knowles Creek, which flows into the Siuslaw River. Today, he examines the flood's effects on the creek and their restoration projects with fish biologist Paul Burns of the Forest Service. Dewberry believes years of high timber harvest have caused increased frequency of debris torrents that scour the channel, destroying habitat for fish.
You just chronically get increasing amounts of material at a shorter time period, and a lot of it gets delivered right into the stream channel because usually the timber is harvested at the mouths of these tributaries where these debris torrents will come out. And so what you end up with is a lot of unstable material moving, and basically that's bad news for most all the aquatic organisms.
Dewberry and Burns walked down the path of a massive debris torrent that originated in a harvest unit 1,000 feet upslope. As it left the confines of the tributary channel, thousands of cubic yards of rock and debris mowed down the grove of alder next to Knowles Creek.
As you can see, it just splatted against this bedrock. The alders just didn't have the capacity to stop and hold it. From here down, we got tremendous amount of damage to the system out of this storm.
On another section of Knowles Creek, Dewberry and Burns examined a debris flow that had a different conclusion. Instead of continuing all the way to the creek, it came to a gradual stop in the tributary channel.
What held it up was 5 or 6 large conifers that were on the fan. And so that's the key function that's missing from a lot of our watersheds now, is they no longer have the large conifer on the valley floors.
As a coastal forest, we're probably more like Alaska than any other national forest in the system. We have a density of something exceeding 1 mile per square mile of anadromous streams that are occupied. Unless the fish have some place to come and spawn effectively, the rest of the system doesn't count for much. So we do feel a very important obligation to try and make sure the habitat is in at least reasonably good condition. Problem is, it's not.
Perhaps the greatest threat to stream habitat on the Siuslaw comes from the road system.
We had built an enormous network of roads on this landscape that was driven by timber harvest. The logging funded the continued maintenance of these roads, and when the logging tailed off, the money dried up. And we could see that coming. The accounts we had were shrinking and dropping radically. We recognized we had to do something differently. So I think we really kind of originated the idea here anyway, that the significant shift had to occur, and we really kind of came up with the idea of stabilizing or storing roads. We ended up with a road system that we will keep open for public travel about 1/3 of our road system. So that meant 2/3 of the roads we had to try and do something different with.
Furnish checks progress on the road that parallels Bear Creek. It's been closed to travel for 2 years and demonstrates the dramatic change in road management.
Now this road is a good example of what I would call one that's transitioning from being in an active, useful capacity to one that we would consider stored, stabilized in a non-use capacity. And so we're seeing it go through some changes. Road has not been brushed to clear it out, surface isn't being graded, and here in a real dynamic environment like the Oregon Coast Range, it's rapidly vegetating back in. This blowdown tree here really symbolizes a lot of the change and transition. If this had occurred 5 or 10 years ago, this tree would not be here now because it would have been very aggressively salvaged. But this log is here and it's going to stay here. Back in the days when you might have had a protection zone of only 25 feet on each side of the stream, this tree would be gone.
They looked for the best way to stabilize a vast road system quickly. Ginny Grilly is the forest engineer on the Siuslaw.
This road was built in the late 60s. The way they built it was getting material from the cut bank and then basically placing it over to create a fill. Once we go ahead and stabilize it by pulling back some of the sidecast materials, we tend to obliterate the road.
They found a simple and cost-effective method for avoiding severe road failures was to improve drainage with water bars.
A water bar is basically a ditch that traverses across a road. It intercepts the water from the ditch and dumps into the fill slope on the other side. It allows the water to more naturally move downslope and avoid concentrating the water in the ditch.
Water barring is relatively cheap, but where fish protection is paramount, more expensive restoration is called for. Furnish goes to inspect progress in the 10 Mile Creek watershed.
Dave Young, this is Furnish.
Furnish, this is Young.
Hi, Dave. We're about 2.5 miles from the gate and anticipate we'll be reaching there in a few minutes. Is that gate locked or is it open? The road system that we have is creating some significant liabilities for us that a storm like this really exposes those and really brings them to bear on you. So we're trying to deal with the road system as we know it today and calm it down a little bit.
In addition to water bars, the Forest Service is excavating major fills and removing culverts, restoring the natural contour of the land.
What size are most of the culverts in this road here?
Most of the ones we're removing are anywhere from 4 foot to 2 foot.
Where we've got liabilities associated with maybe a small culvert, a deep fill, sooner or later that's going to fail. And we didn't feel we wanted to be prepared to live with the consequences of all that soil moving down into live water. And I really see a profound change occurring. And to me, it really relates to how we as managers view the resources we manage. The magnitude of that issue on a forest like the Siuslaw, where the timber values alone, just economically, the timber values of the standing forest here as a timber product is probably $20 billion. To me, that's a big number. And I'm struck by the view that that is equally as valuable for fish and wildlife habitat as it is for simply processing as wood products. For us, that translates into, say, a reduction from harvesting over 300 million board feet a year on the Siuslaw to now, under the Northwest Forest Plan, 25 million board feet, more than a 90% reduction. And yet feel that that trade-off is worthwhile given the tremendous wildlife and fish resources we have here. Most of the remaining natural forests are on federal lands. That to me says that we have a particular niche to fill in this ecosystem, in this environment. I think if you look at the problems that we're having with salmon and the tremendous density of anadromous streams that we have on federal lands on the Siuslaw National Forest, if anybody should be expected and have almost a moral obligation to make sure that we're doing everything we can to try and provide the best possible habitat for salmon, it ought to be us.
The flood of '96 brought a torrent of change to the forest and the streams that sustain an abundance of life. The storm gave us a chance to explore the manner in which large-scale change takes place.
These events happen maybe once in a career. And so the time scale of these natural events and the time scale of human lifespans and career spans means that one person is only going to have a limited exposure, if any, to something like this. And so it becomes, I think, really important for those people for whom something like this has happened to leave a legacy behind that other people can learn from. And that's a legacy in scientific information. It's a legacy in terms of going out afterwards and asking what worked and what didn't. It's the kind of learning mentality that comes easily if you're in a research setting. But it's not unique to research. And in fact, the distinction is less clear than a lot of people, I think, like to make it. If we're really serious about adaptive management, then you have to have some process to capture what it is you know, to learn from your mistakes, and to come back and do things differently. That works in science, and it works in management.